Are those, the quizzes are floating around. The graded quizzes are floating around. So make sure y'all get those, keep those going around. All right, how's everyone doing?
Good.
Y'all ready?
Yep.
Okay, so like I said, some of you just got here. I do plan on doing a quiz at the end of class, but I don't intend on giving quizzes every single day. But I just want to make sure you're staying at least at some baseline right now. The quiz that I have for you today, I think, is on a scale of like 1 to 10. It's probably like a 3. So it's just to like keep you honest, that's all. But we'll get to that later. So we are going to cover a few things before we jump into the next section. I just want to make sure we're clear on a few things. So take a look at these integrals here. Let's look at that one. Let's look at that one. Let's look at that one. All right, so all of these integrals are similar, but they're different. There's slight little tweaks that we would have to make for each of these if we're going to find the antiderivative. So what about the first one? Now, what's the antiderivative of cosine of x? Just sine x, right? Plus c, and we're done. There's nothing else to really concern ourselves with here. This is kind of like directly from Cal 1, we know this. Now the second one does not work that way because of the 2 inside, right? The argument of this cosine function, 2x, would cause problems if we said that the antiderivative was just this, right? If we said that, then it wouldn't be true because when we take derivative of this, we'd actually get cosine 2x times 2, right? And this doesn't have a 2, right? So what we would have to do this problem, I'm not going to go through the work, is make a little substitution. U is equal to 2x. du would be, and I'm going to stop doing du dx. I'm going to start just putting the dx over here every single time. Yes, James?
You wouldn't want to change that into its double angle?
I mean, you could, but I mean, sine 2x, no. Yeah, just substitution. This is all, why did I put x here? Sorry. The derivative of 2x is just 2 dx, and then you just replace the dx. So you'd have to scale both sides by 2. Right? So basically what we're missing in front of this is a what? A 1/2. Okay? Now, how about this one? So we still have the idea that the antiderivative should involve a sine of 2x plus 5, right? But if we would take the derivative of this, we would get cosine of 2x plus 5, but then times what? Times 2 again, right? And so we would need to get rid of that 2, so we would need to scale it by a half also. So if we did this problem through basic U substitution, our substitution would be 2x plus 5, and then we'd work through it the same way we did this one. Does that make sense? Okay, so would that have worked for this? I've been very careful about what I've put inside here. Would that have worked? Same idea here. So like you might think this is just sine of x squared plus a constant. But because you have to do chain rule on this, the derivative of what's inside would give you a what? A 2x, right? A 2x. So you might be thinking, oh, I have to scale by 2x, like 1 over 2x. You might think that that's the way to do it. But this isn't going to work. Because if you now differentiate this, you have to use the product rule, because you have a product right here. So this does not work. So this idea right here that I'm trying to get you to see only would work, I'm trying to see if anyone can tell me, when this idea of just scaling out would work. This inside here would have to be what?
Have to be some sort of constant.
Constant times x?
Just a single variable.
Single variable, right? Not raised to a power. So a linear expression. Let me write that, let me put that in a different way. What we're trying to see here is that if we had antiderivative of cosine of an arbitrary linear expression in x, right? That's a linear expression in x. Then the antiderivative of this should be sine of ax plus b plus some constant, right? But because when we take the derivative of this, we would get what? What would be the derivative of this right here? A, we would need to scale it by 1 over a out here. So we would need a 1 over a, wouldn't we? And that should work for any linear expression we have inside this. Now look back here. What, is this a linear expression? Yeah, what's the coefficient in front of it? 1. So you would have to scale this by 1 over 1. So it works here too. But it works here and it works here. With me? Okay, so let's see. Can we extend that to, would this work for like any of the functions we know? Let's try something else. How about antiderivative of e to the negative 5x plus 1 dx? So that's e raised to a linear expression in x, right? So if we know the antiderivative of e, right? What's the antiderivative of e to something? Should be that e to that something, right? And then plus a constant. But we could check this, that if we took the derivative, we would get itself, and then times the derivative of what's up here, which would be negative 5, but we don't want that negative 5, so we'd have to scale by it, right? So we would need like a negative 1/5 out here. Is this making sense? Yes. So what would be a more general formula like this? What could I write here as a more general formula? E to the what? Ax plus b dx. The antiderivative of that should be what? 1 over a e to the ax plus b plus some constant, right? And we can do that for every single function we know the antiderivative of already. As long as the argument of it is linear, we'll always have to scale out by that coefficient on the x every single time. Let's see if we can get one more general formula. I mean, we could keep going with a bunch of them. What's something else we know? How about, I don't know. How about secant squared of ax plus b? So using the same concept here, the antiderivative of this should be what? 1 over a tangent of ax plus b plus c. Okay? So just keep that in mind as we move forward. If we are doing the antiderivative of something we know, but the thing inside of it is a linear expression, we just need to account for that when we take the antiderivative by scaling by 1 over a. All right? Okay. Now we're ready to move on. One of the main themes of last class and of kind of the rest of this class, and I think I talked about this a little bit last time, was that when you're doing like the U substitution, 5.5, when you're doing that section, that there's no like cookie cutter way of doing it, right? You have to try something, see if it works, and I think I made that clear, did I? So I know some of y'all are subscribed to my YouTube channel, so you get updates when I post videos. Right now, I'm not teaching differential equations right now, but I plan on teaching it probably, hopefully in the fall. And what I'm doing right now is I'm going through the whole book and I'm doing all the problems, and I'm doing them on video so that when I teach the class, my students will have the solutions to the homework, right? So I'm working through this, and I mean, honestly, it's been a long time since I've taken differential equations, so it's been fun, but it's taken me a while to get through it. This one particular section, I thought it was interesting. I was reading the beginning of it, and it says here, just ignore some of the details, just pay attention to a few keywords. An equation may look different from any of those we have just studied. but through a judicious change of variables, perhaps an apparently difficult problem may be readily solved. Although we can give no firm rules on what, if any, substitution to use, a working axiom might be, quote, try something, end quote. It sometimes pays to be clever. So this again is, the beginning of a differential equations book is kind of the same theme that we have right now, which is there's no like systematic process that you're going to be given. You just have to try something, right? And then if you're clever enough, which comes with experience and practice, then it may pay off, all right? So just keep that in mind as we move forward. Also, I'll show you that the problems that I worked out of this section, what we're doing today, actually, I had to use that in these problems, and I'll show it to you after we get through this a little bit. Okay, so integration by parts. So I said at the beginning of this class that there's going to be, our main goal for the first third of the course is for us to be able to find antiderivatives. And so far, we have just a few ways of doing it. We recognize it from Cal 1, right? So it's something we are familiar with, we've seen it, so we can go backwards, find the antiderivative. We have the power rule, right? If it's x to a power, we can do it. We have substitution, which is what we covered last time, which is we look at the integral, we try and identify something in its derivative, and we hope that its derivative isn't trapped or in the denominator, and it's okay to be off by a constant. So all of you went home, did all that homework, you know what I'm talking about now, right? Yeah. So we should all be somewhat comfortable with that as we move ahead now. So now we introduce the next kind of idea, and this is integration by parts. This is like the first big method, all right? Integration by parts. After integration by parts, we're going to be doing what are called trig integrals, and then we're going to be doing trigonometric substitutions, and then we're going to be doing partial fraction decomposition. So those are like all of them in, like, I'm summarizing everything. This is the first like major one. Not to say what we've learned isn't major, but to do these problems, you'll have to know everything we've done already. So we'll be getting a problem basically down. We'll start with a hard problem, and we'll try and get it down to something that we can handle now, right? All right, so this is a formula, all right? This is an actual formula. It's the only time we're going to have a formula. And it comes from the product rule from calculus. So I actually like to write this out. So if we sit here and say that u is a function of x and v is some other function of x, right? So we have two different functions, f and g. Very important that you understand these are two different functions. Then we know from Cal 1 that if you look at the product of those two functions and you take their derivative, right, that you have to use the product rule. So this is going to be the derivative of u times v plus the derivative of v times u. And we talked about how you might have learned this in a different order, but we all agreed that that's correct, right? So from this formula, we're actually going to create this thing called integration by parts. And the way we do it is, what we do now is we integrate this. We take the antiderivative of this equation. Okay, so what would happen if we take the antiderivative on this side? Let's do that one first. So what's the antiderivative of the derivative? Well, these are kind of like inverse operations, aren't they? It's like you take the derivative of something, and then you take the antiderivative. So it should just just leave it unchanged, right? This should just be u times v. Y'all agree? Now on the right side, we're going to take the antiderivative of a sum, right? So that means we can take the antiderivative of each one separately. So if I take the antiderivative of this one, I'm just going to write down what I have, plus the antiderivative of this one. So I'm just going to write down what I have. That's just using the fact that the integral is linear. You can do them separately, just like you differentiate term by term. You can do antiderivatives term by term. And believe it or not, this is where the formula comes from, that equation right there. So I'm going to rewrite this. Okay, I'm just going to rewrite this, and the way I'm going to do it is I'm going to write it like this. I'm going to write integral u times v prime. Okay, so that's this one right here, but I flipped that around. Agreed? Okay, now what I'm going to do is I'm going to take this integral to the other side, so I'm going to subtract this integral on both sides of the equation. All right? So this integral moves to the left. Algebraically, that just becomes, well, let's see, what's still on my left-hand side? I have u times v, but I've now brought that integral over, so I have minus integral and then u prime v, right? U prime v. I'm going to write it backwards. V times u prime. Okay. Now I'm going to just do one more thing and we'll have our formula. I'm going to just write v prime and just using a different notation. Instead of v prime, I'm going to put dv, like the derivative of v, okay, dv. And then here, I'm going to leave u times v, and then minus, and on this one, I'm going to rewrite this one, v times the derivative of u, I'm going to write du. And this is the formula that we will use right here. So that's where it comes from. There's a little like verbal saying that I know some of you have heard it before. It's ultraviolet minus voodoo. V-O-O-D-O-O, right? Yeah, okay. Okay, so this is a little saying. It's very catchy. You won't forget it once you learn it. Ultraviolet minus voodoo. And what this formula does is it allows you to remember this. So do you all see this is ultraviolet minus voodoo? Now, you have to remember the integral here, okay? That part you have to remember. But ultraviolet minus voodoo is just a nice, quick, easy way to remember the formula we're using, all right? So right now, all I've done is I've shown you, hey, look, if this is true, then I can do this, and we have this formula, right? But let's talk about why this formula is useful, what it's doing, what it allows us to do, right? Like, why is this useful? So I remember distinctly learning this. Dr. Richardson is the one who taught, that was my teacher when I learned this. And he just beat this into our heads. I'm going to try and beat it into yours the same way. So we start with an integral, right? Which is where we've been starting all of our problems. We start with this integral. And then notice that this equation allows us to turn that into some stuff. Do you see an integral here? No integral here, right? No. But then minus this new integral, right? Are these two integrals the same integrals? No. Well, this one has u in it, right? What does this one have in it? The derivative of that u, right? And this one has the derivative of v in it, and this one has v, which would be the antiderivative of that one, right? So let's take a look at what's happening. If you start with this integral, here you have some function of x, right? Remember this was some function of x? Remember that? I wrote that up here. U is f of x. And I told you that g was what? G was v, right? V was some function of x like this. So what this is saying is that if you start with an integral where you have some function of x times some other function of x, but it happens to be the derivative of something. Do you all see that? I just said the derivative of something. Okay, be careful. What was u substitution? U substitution was you're looking for something, right? And its derivative, right? And its derivative? That's not what this is saying. This is saying you have some function here, right? And next to it, you have the derivative of some other function. Right? Not this function, some other one. This formula allows you to transform this integral into a new integral that will have up front here u, which is f of x, which would just be that function, right? And then it has next to that v, and what's v? G of x. And then over in the new integral, you have v, which is g of x, and then next to it you have du, which is the derivative of f. So Dr. Richardson said, Look, what's happening here with this formula is that you are transferring the derivative. You are transferring it. You are transferring it in this integral. There's no derivative on f, but in the new integral, you have the derivative on f. And then over here, you have the derivative on g, but here you've transferred it over and you've taken g back to its antiderivative. Do y'all see that? So why would this be useful? Like, it doesn't seem like this would help, but you have to see an example, all right? See an example worked out, and then you'll appreciate it. I hope. All right, so here's your first example. I'm going to leave that up there. There we go. X times cosine x. X times cosine x. So let's talk about the things that we knew walking in today. All right, we knew that if this looked like something from Cal 1, that we could just go backwards, we just do it, right? Well, we can't because it's not just cosine x, right? And it's not just x. If it were just x, power rule, right? If it were just cosine, antiderivative sine. If there were a plus between them, we would just do them separately and be happy. But there's a multiplication. So we can't just undo them. So someone on the test, someone, don't write this down please, somebody on our next exam is going to put this. Do you all see what they did? They just took the antiderivative of this one and then this one separately and multiplied. And you can't do that. And if you don't believe it, just take the derivative of this now. You're not going to get that, all right? So this won't work. If there's multiplication between the two functions, you have to try something else. So it's not something we recognize. How about a basic u substitution from last class? Do you see something and its derivative?
No.
Not really, right? I mean, I can't let u be cosine x because the derivative that's negative sine x, and I don't see negative sine x there, right? Could I let u be x?
No.
Why not? I told you never to let u be x with u substitution. Because what happens, you just rewrite the whole problem. And everything's u's instead of x's. So you can't do basic u substitution here. At least it doesn't look like it will work, right? So we're kind of stuck. However, maybe this will work. So maybe we can look at this as some function of x, right? X by itself. So let's say we let that be the f. Let's say this right here is our f of x. Then what would the cosine x have to be?
G of x.
That would have to be,
G of x.
not g of x, the derivative of g. So this right here, and I'm going to include the dx because when you take a derivative you have chain rule. This would have to be the g prime, wouldn't it?
Yes.
Do you all see that? Now, if we do that, let's think about what the new integral would look like. I know I've got some stuff here, right? This is my ultraviolet, but let's just consider the new integral, because this is the most important part of the whole technique. In this new integral, what would appear in here? G, which would be the antiderivative of cosine x dx, which is sine. Would we mind seeing sine in there? You know, if it's there, right? But here's the key. What else is in here? The derivative of f. And if f is the function x, what's its derivative? 1. And then, so in here we're going to have sine of x times 1. And that's just sine x, right? And can you integrate sine x? Yes. So if we kind of like take a step back now and look at this, it's like one of these guys, we're going to pick, right? One of these guys, we're going to have to take its derivative and put it over there, right? And the other guy, we're going to have to take its antiderivative and put it over there. And we need to kind of think about what that would look like if we did it. Because you could have chosen it the other way. There's nothing saying that you have to make the first one f. So I could have done it this way. I could have let this piece be my f of x, which would have forced what to be the g prime? I would have had the x dx would have been my g prime. Now, would that have been a good thing or not? Think about what it would look like in the new integral. you would have the what of this in the new integral? The derivative, right? Which would be negative sine x. That's okay, right, to have negative sine x? I'm going to throw it in here. Negative sine x. I'm not too, afraid of that. That seems okay. But what would be in the new integral over here? The antiderivative of x dx, which is 1/2 x squared. So now you're going to tack on next to this times 1/2 x squared, right, dx. Now this integral has now just become more complicated than the one we started with. Because initially we just had an x in front of the trig function, right? But by doing it this way, now we've got an x squared in front of a trig function. So do you agree this has gotten worse? Okay? So there's no way to know which one to pick without you actually kind of thinking about it a little bit first. All right, do y'all kind of get the idea? Now I'm going to work through this problem from the beginning, start it completely over and show you how I do them. All right. So starting with this, x cosine x dx. We're going to use integration by parts. So whenever we do integration by parts, IBP, integration by parts, I'm just letting everyone know that's what I'm about to do. And so what we have to do is we have to choose which one of these is going to be the u, right? And which one of these is going to be the dv. Or which one's going to be the f of x and which one's going to be the derivative of g. So I do it this way. There's many different ways to teach integration by parts. It's the way I do it. I always make a table. And in this table, in the top left, I put u, and in the bottom right, I put dv. Okay, that's where I'm going to start. I have to make that choice first of which of those functions is going to be the u and which one is going to be the dv. So we already went through this, right? So u should be the what? The x, right? U should be the x, and the dv should be everything else that's there, including the dx. So this should be cosine x dx. All right, that's the choice you make, right? Now the rest of this is just completing this table. And the way the table works is this. If you go down this table, you're differentiating. If you go up, you're integrating. So if I take u and I take the derivative on both sides, I get du equals what? 1 dx, or just dx. Okay, just remember you need to write the dx here. Y'all agree with that? Differentiate down. And now integrate this up. So if we integrate up, what's the antiderivative of dv? Just v, and then antiderivative of this would be sine x. Now you're supposed to put plus c, right? But we're going to just throw a plus c at the very end of our problem. Like when we're done, we'll put plus c, okay? All right, do y'all understand this table? All right, so now we're just going to do ultraviolet minus voodoo. So we're going to take this, I'm going to get rid of this. So this becomes, I'll put it over here, ultraviolet minus the integral of voodoo. Okay, so I'm going to do u times v first. So here's u, right? And here's v. I just need to multiply them together and stick that right there. So this is going to be x times sine x, right? Okay, minus the integral. And now I'm going to do voodoo, which is this one times this one. Those two multiplied. So what's that? Sine x dx. You see, if you don't put dx, then you're not going to put dx here. It's just bad notation. So sine x dx. And then you look at this integral, you kind of reevaluate it, and you say, can I do that integral? And in this case, we can, right? And so the antiderivative of sine is what? It's the antiderivative of sine. So we have a negative here, right? So the antiderivative of sine is negative cosine. Agreed? So minus cosine of x, and then our plus c here. And when we have minus minus, it becomes plus, right? And that will be our answer. X, well, it's supposed to be. How would we know for sure? Take its derivative, right? So what we're saying is that if we take the derivative of that, if we do, right, what should we get as an answer if we take the derivative of that? X cosine x, right? Let's check it. I want to check this one because it's the first one we've done. Because that's kind of an ugly looking thing to think that its derivative would just be x cosine x, right? Okay, so I'm going to take the derivative just to check. If I take derivative, I have to realize there's a product right there, which is a product rule on those first two. So that would be the derivative of x, which is 1, times sine x, plus the derivative of sine x, which is cosine x, times x. That's finishing the product rule. So that's our product rule on that. Then we move on to the next one, plus the derivative of cosine of x, which is negative sine x, and then the derivative of the constant is 0, right? And do you see that this negative sine x and this positive sine x cancel? And all you're left with is x times cosine x, which is the original integrand, right? So it works. Transferring the derivative is what we're doing. Transferring it, hoping for a better looking integral, something we can handle. Anyone have any questions? Okay, I have all of these examples that I want to work through.
Sir,
Yes?
if we had another product function right over there, do we have to do it again?
If we had, oh yeah, we're going to do that. That'll be part C.
Oh.
Yeah. Yeah, when we do C. Look, so I'm about to show you different sorts of scenarios that you can run into when you're doing integration by parts. This first one that we're going to do is a basic integration by parts. The next one's, what I'm saying, is a not so obvious one. This third one is going to be a repeated, and then this one is the rabbit out of the hat. This is a weird one. This one, I just added this one to the notes today. It's not that it's hard, I just want to make sure I cover it. And then, yeah, so let's just start with the first one. This first one should look very familiar, right? Because we just did one very much like this. Didn't we? Yeah. Okay, so you always want to exhaust the other methods first. Is this something you recognize from Cal 1? Can you do it with a basic U substitution, right? Those things have to, I always think of like a little Rolodex of ideas. Y'all know what a Rolodex is? Yeah. I don't even think people have Rolodex. What the? That's an obsolete thing, right? It's like a thing that used to have cards in it with people's names, like you keep addresses and stuff. You'd roll through it. I never used one. I don't know why I'm still using that terminology in here. But so you just want to kind of like go through all of your different methods, make sure that it's not something easier before you get to this. All right, so we have to make a choice, don't we? Nicholas? All right, Nicholas. Are you seeing integration by parts here? Okay, if you see integration by parts, you've got to choose one of these things to be your u and the other one's going to be dv, right? So which one would be your u? The x. Why? Yeah, so if you're choosing x to be the u, in the new integral, it's what?
1.
It's a 1, or dx. But it gets better, doesn't it? It gets nicer in the new integral. And that's usually a good indication that you should use that for your u. So I'm going to let u be x, and then that forces you to let dv be what? Everything else that's there, right? Sine of 10x dx. Okay, now you're just going to complete the table. Differentiate down, integrate up. So we differentiate down. I'm going to let Juan, I need to get through everyone today. So Juan, where's Juan? Okay, Juan. Okay, differentiate down. So what's going to be here? What do I write?
dx. 1.
Okay, so du equals dx, right? Okay, and then here we're going to integrate up on to v, right? So now you have to know what the antiderivative of this is. So just, you can kind of almost visualize like an integral sign in front of that. You feel comfortable with it?
Yeah.
Okay, what do you got?
Negative cosine.
Negative, close.
Cosine.
Negative cosine of, So we just talked about this at the beginning of class today. This is a linear expression inside of sine, right?
Yes.
So because it's linear,
That's 110.
1/10, there you go. Okay? Everyone agree? So we have the antiderivative of sine of negative 10x. I'm sorry, sine of 10x is negative 1/10 cosine 10x. And now we just rewrite the problem using ultraviolet minus Voodoo. So Adam, where's Adam? Okay, Adam, I want you to tell me what that integral up there, I'll write it, is equal to what according to our formula?
U
X times this, right?
yeah, the
Okay, so let me write that down. I'm going to write it this way. Negative 1/10, I'm going to put the constant out front, then the x, then the cosine 10x. You agree that's a pretty clean way of writing it there?
yeah.
Okay. And then you said, I'm going to do what?
You subtract the
Subtract from that the integral of
v
v times
du
du. So these two multiplied,
dx.
right? So you're going to have negative 1/10 cosine of 10x. I'm going to run out of room dx. Agree? Okay. Let's see. Al, no Al today. I even put a little note here to pronounce this right. Is it Rifa?
Yes.
I said that right now?
Right?
Rifa. So that's an I? I. Yeah, I put I here. I'm going to stress that. Okay, Rifa. Rifa? What the hell am I doing, Rifa? I forgot. I'm going to rewrite this integral, okay? But before you do an antiderivative, I just want you to help me clean it up. How could I rewrite that to kind of clean it? Is there anything I can do with that minus 1/10 on the inside? Rifa. See this minus 1/10? What can we do with constants when we're doing antiderivatives? Take them outside. So if I brought this outside, this would just become plus 1/10, right? So why don't we do that? We're going to put plus 1/10. And then now we have to do the antiderivative of cosine of 10x dx, right? But do you feel okay with that?
Yes.
Okay, so I'm going to go to the next line, rewrite everything, negative 1/10 x cosine of 10x plus 1/10, and then Rifa's got our antiderivative here. What is it?
1/10.
1/10 sine of 10x.
Yes.
Plus e, good. There we go. So we had the 1/10 from here, but then because we're doing the antiderivative of cosine of a linear expression, we have to do another 1/10 in front of the sine, so that those are going to wind up going together to give you 1/100th, right? I think I'm ready for my last line. Okay, my last line is negative 1/10 x cosine of 10x plus 1/100th sine 10x plus a constant. There we go. That is our antiderivative. And you could check it, couldn't you?
Yes.
Should we or no? We checked the last one, right? This one would work the same way. You have a product rule right here. So you do your little product, and then you take derivative here, and things will cancel. And you should just be left at the end with x times sine of 10x.
Wait, Mr.
Yes?
DiGiovanni, before you erase it,
Okay.
can you repeat again like how you multiplied 1/10 by the 1/10?
Like why? Okay,
Yeah,
so
so-
we're ignoring completely everything here. Like just ignore all that. Okay, and just do this piece right here. So the antiderivative cosine of something is going to be sine of it. But remember, because this was linear inside, you have to scale it by 1/10.
Okay.
But that's being multiplied by this, right? This is multiplication. So you've got to put that 1/10 together, multiply, and get your 1/100th. Good?
Yes.
Okay. All right. Y'all ready for the next one? All right. The next one not so obvious. Okay, so you go through your little mental Rolodex, and you exhaust all the other methods. You're like, okay, no, I don't. You know the derivative of arcsine, right? But that's not what we're asking for. Basic U substitution, I don't think that's going to work. So Hogan, you're up. I had a question for you again.
Yes, sir.
So if you're doing IFR, is that what it's called?
Yes,
IFR? Do you that means you have to like file a flight plan, and those take time, and
Yes, sir.
so you can't just be flying and all of a sudden go to IFR.
Well, you can, but you have to call air traffic control.
Yeah.
You say, hey, I'm requesting IFR.
Yeah.
But they don't like to do that because that causes
Yeah.
hustle. It's making the radio.
Okay, that was it. Thank you.
Yes, sir.
Okay, so Hogan, if everything that we know doesn't work, and the only other thing we have is integration by parts, then that forces you to have to make a decision as to what U is and what dV is, right? You have no other choice. So
You. Let's see, you. Like, can you somehow take the pi x out?
can't do the pi x out because it's the argument of the inverse trig function. There's nothing we can do algebraically to get that out.
One.
You could look at it as a 1. Just outside next, you could look at that as being like, I mean, you could look at it that way if you want. I don't know. Yeah? So if you look at it that way, then make a choice. What do you want?
So would you multiply it by u equals 1 dx?
Okay, so let's try that. If you did this and said u is 1 dx, then what would dv have to be?
It would have to be arcsine of pi x.
Arcsine of pi x, right? Now there's several problems with this.
Yeah, you can. Yeah.
First of all, your dv always has to have the dx in it, always, because you've got to integrate that, right? And that means you have to have the dx out here. So you can't have this here, okay? Can't have the dx here. Could we do this? I mean, could we let that be 1? Do you see a 1 there?
Yes, sir.
Could we let dv be everything else?
Yes, sir.
Sure, but what's wrong with this?
It's the same problem.
It's the same problem. Yes, you could differentiate that down and get 0, right? But when you integrate this up, what are you asking? What's the antiderivative of this, right? Which is exactly the original problem. So that doesn't work. So let's see, you have to have dx here, don't you? That's what I just said?
Yes, sir.
Okay, so then that forces that to be what?
Oh, arcsine.
There you go. Now you have to ask yourself, do you know what the derivative of arcsine of pi x is? The derivative of it.
Arcsine.
Right, we know, I mean it's in a formula sheet, but we know that, right? Like we can differentiate, we just can't integrate it. So I think this is going to work. Do you see that that's going to, okay.
You gotta break out of the habit, like you said, you gotta apply it.
Yeah. Okay, so let's try and complete the table. Any questions on this? This is the first time we've ever let dv just be the dx. It's the first time we've done it. And then here, we're going to just differentiate that thing down.
So dv always has to have dx.
Always has to have the dx in it. You can never let u be the dx, right? Never, because then you'd have to differentiate dx, which would be like a second derivative, but then you would have to integrate something without the dx in it, and that you can't do. So yes, dx will always be on the dv. But it could have more with it. Okay, like in the previous problem, it was like cosine dx. Yeah, cosine x dx. All right, let's go ahead and complete the table. So when we differentiate down, du will be equal to, well, you have to know what the derivative of arcsine of x is, or you need to know the formula, where it is in your formula sheets. This should be
1 over the square root of 1 minus pi x squared.
pi x squared. Now, be careful here because we still have chain rule, right? So you still need to now take derivative of the argument. What's the derivative of the argument? Oops, I forgot to turn off my phone, sorry. It'll be just pi, right? Yeah, we can put the pi on the top. Does everyone clear that we have a pi out here and dx? Pi dx is right here, but we're going to slide that pi up top, just because I'm almost out of room. So that is our derivative, yeah? And now we have to find the antiderivative, right? To get up to v, we have to do the antiderivative of 1, which is just, that's the derivative, careful. We're antiderivative, this is going to go up and become x. Right? Yeah, so now this may not look like it's better. Okay, I would say this doesn't look very nice because we should be thinking, as we're doing this method, we should be thinking like, at the end of the day, we have to integrate Voodoo, right? Voodoo, and this is your Voodoo. And right now that may look terrible, but let's just keep going. Okay, so that integral now becomes ultraviolet. So these two multiplied, right? That's just x arc sine of pi x, okay, minus integral and the v times the du, right? I'm just going to write it out. Here's the v times the du. Okay. Do you all agree that that's where we are? You have to be able to integrate this now. And when you're looking at it, I would agree with you that this doesn't look very good. This is pretty intimidating if, if we're not real comfortable with things yet. This is not something that you're enjoying seeing. However, we can integrate this. Now, I think it's easiest to see if you let me clean it up a little bit first. So one thing I'm going to do there is take that pi and just pop it out. I just always like to pull constants out. I don't know why, I like to. The x can't come out though, right? Only constants. I still have an x. I'm going to leave that on the top, x. And on the bottom, watch what I do with the bottom. I'm going to write that as 1 minus pi squared x squared. And then dx. So all I've done is I've actually applied the squared to each of the factors. So it squares each one. Luke? Okay, Luke. Are you with us so far, Luke?
A little bit.
A little bit? Okay. I'm telling you that this can be done, okay? And I'm going to also tell you that it can be done without integration by parts. So it's something else that you... Okay, so u substitution. What's the u?
The bottom.
What do you mean the bottom? Say what it is.
1 minus pi.
1 minus pi squared x squared. That'll work. Because if we take the derivative of 1 minus pi squared x squared, the derivative of 1 will be 0. And the derivative of this is going to be ugly, but it's going to be something times x, isn't it? Because the power on x comes down, or the power on the x2 comes down. This is just a constant in front. So we need to all realize that when we take derivative of this term right here, we're going to get some linear, some number in front of x. And up top we have x. And so we're off by a constant, perhaps. Does everyone see that? Okay, so let's do it. Let's make that substitution. So it's almost like at this point in time, we're stepping to the side and we're doing some additional scratch work. So I'm even going to do that and change colors. I'm going to say SW for scratch work. I need to figure out what this integral is. And Luke said we're going to make a substitution. U is equal to 1 minus pi squared x squared. The derivative of that, Luke, do you want to tell me what the derivative of that is? So what's the derivative of 1? Okay, negative pi squared is a constant, right? So it just comes for the ride. And then take derivative of x squared.
1/3.
Oh, you're doing antiderivative, right? Because we're doing u substitution, so we're going derivative.
2x.
2x, right? So I'm going to write it this way. Negative 2 pi squared x dx. Okay, so right here, this part that I'm doing here is u sub from last class. Making a substitution, taking its derivative, and trying to match things up. So we don't have, in our integral, we have down here, this is going to be u, isn't it? This right here is going to be u. And now what we need to do is somehow replace the x dx with something. So we have to, here's x dx, so we have to divide both sides by negative 2 pi squared. This is fun. Okay, so we're going to do negative 1 over 2 pi squared du equals x dx. So I just multiplied both sides, or divided both sides by negative 2 pi squared, and that's what I get. I'm running out of room. I'm writing too big today. I don't know why I'm writing so big. All right, I've got to continue. I'm going to leave this here because that's where we were, right? This is where we were, and I think I can get rid of this table. So I'll continue over here. So one drawback to filming my classes, I got to stay in this little space. It'd be nice if I could just go around the room. But okay, so now I'm going to go, and this integral now becomes, I'm going to make the substitutions, right? So I have integral, let's see, 1 over what? Square root of u, right? And then this x dx turned into this. So I'll just write it down. Negative 1 over 2 pi squared, what the hell, du, right? I'm going to pull out the negative 1 over 2 pi squared out of the integral completely, and I'm going to rewrite this as u to the half, and then I'm going to bring it up. So my next line is going to be negative 1 over 2 pi squared integral u to the negative 1/2 du. And now I can, Herman, now I can, what can we do with that, Herman?
Where are we at right now?
We're right here. So I pulled that constant out, I rewrote that as u to the half, I brought it up, u to the negative 1/2. What technique can we use to solve this?
Antiderivative.
Okay, what rule?
Power rule.
Power rule. Okay, so we're going to go, we'll bring the constant with us, times, and now we add 1 and do that little thing, right? So adding 1 to this, we get positive half, and then 1 over a half, that becomes 2, and so we get u to the positive 1/2, something like that. Plus c, but we still have a lot more problem to finish. So once we finish everything, we'll put plus c. Good? These two's cancel. And what was u? U was this, right? U was this. So I think I'm ready. I think I'm ready to come back to this. Are y'all ready? Okay, here it comes. So my next line over here should be equals x arc sine of pi x. Okay, minus pi. And now this right here, we just did, right? And that gave us this answer at the end of it all, right? That's going to get inserted right here with multiplication. And I've got to make sure I got all my constants in here. I'm going to have negative 1 over pi squared times u, which is this, to the half, which is the same as the square root, right? So I'm going to put square root of 1 minus pi squared x squared. There it is. Now plus c. And there's still a little bit more algebraically we can do, right? Like that minus minus becomes plus, and then one of these pi's cancels. I say cancel. That's incorrect. It's actually called reducing, but you'll hear me say cancel. Some math people get really offended by that, but I'll let the math gods deal with me later. Okay. There we go. That's it. The antiderivative of arc sine of pi x is x times arc sine of pi x plus 1 over pi times the square root of 1 minus pi squared x squared, plus c. So we could check, yes? We could check. We could, we will. Now, I'm not going to require you check all your work, but it is nice to see that this all does work. So I'm going to check it, right? I'm going to take the derivative. I'm going to go fast. Okay, here we go. Fast derivative. Product rule, right there. Otherwise, I'll do this one separately. This is just really the square root derivative square root of something, so I can handle that. All right, product rule here. Derivative of that is 1 times arc sine of pi x. Okay, plus derivative of arc sine of pi x. We did that, didn't we? We did that while we were working through this problem, and it came out to be this. Right, I already squared that piece, and then we still had a pi, didn't we? Because chain rule. And then we still have to multiply that times x, because product rule. So I'm just going to put that pi x on top, just to make my life a little bit easier, save some space. Okay, that's it, right? I'm done with the product rule. Okay, now I need to take derivative of this. So plus 1 over pi, now times, the derivative of the square root of something is 1 over 2 times the square root of that something, whatever it was, times chain rule, derivative of what's inside. What's the derivative of what's inside here? This is what Sherman did. Or who did that? Luke? Who did this? Oh, who cares? Negative 2 pi squared x, right? That was the derivative of what was in here? We done? Yeah, derivative constant 0. So let's see if this cleans up. We got this, one of those pi's, one of those pi's. Holy shit. So look, this right here is pi x over the root of that junk, right? And this one right here is negative pi x over the root of that junk. These are exactly the same. They're just off by a sign. Agreed? So that cancels with that. And all you're left with is the front side, which is arc sine of pi x. Right? Right. Works. So I told you a while back, it's good news. You can always check your answers, right? But that obviously it's not that great a news, is it? Because sometimes those derivatives can be a little bit. I don't think that derivative was that bad. All right, next one. We switched up the variable. We're using t instead of x. No big deal? Okay, we have b, or beta, I should say. We have beta in front of t. Beta in this problem is a constant, which means it's a number. You may as well look at beta as being the number 5 or the number 2 or something. It's a constant. And while you're doing your homework, be aware that when you're doing these, we can determine what the variable is by looking here, right? dt tells us what the variable is. So we can assume that beta here is a constant. So if you see like a or b or something like that in the integral, I think we were talking about that earlier today, right? The a or the b, those are constants. Okay. All right, who is going here? Wait a minute. I already called Hogan. What the hell? It's just Shay, right? Yeah. Okay, Shay, what do you got? What are you thinking? Tell us what you're thinking.
I would pick u as t squared and then dv as, or
Yeah.
dv as cosine of beta.
So u equals t squared, and dv you want to be everything else. So cosine of beta t dt, right? Now, do you have any ideas to why you think that's going to work?
No, I think it'll just turn out cleaner.
So in the new integral, you're going to have the derivative of that, which would be 2t. And the antiderivative of this, which will be sine with some crap with it, right? But it'll be sine. So your new integral is going to have t in it and sine of beta t with some constants. But you'll still have the t in front, won't you? But you won't have t squared, you'll have t. Which means you might have to do what with that new integral? Maybe do it again. You might have to do integration by parts again to kill the t off. So let's just back up and think about that. Because this is t squared, we know if we do one iteration of integration by parts, we're going to be able to basically